Watch the video, right?
Yeah.
Okay. Yeah, well, if you're like period 6, we got a lot of questions. 911. Okay, that's not even funny. That's not even funny. There's no way we're gonna, because we got electric today.
How many more electric?
You guys better revise that right now. Okay, no.
How many more electric do we have for this chapter?
Anyway, okay, wait, stop. Didn't I give you an example yesterday of 1 and 2? Okay, number 3 I can understand.
3D. Okay, so 3
But number, okay.
How about 1 and 3?
1, 3.
No, we're not gonna do all of 1.
Shout it out, shout it
Here
out.
you
I will do 1A or B. Pick one.
B. Actually A. Wait, I don't know.
1A.
Let's just do both really fast.
We're not, they're both exactly the same except different.
The same thing.
Okay, choose
different.
B.
B.
Right.
1B.
So B, because it's more things.
Okay, now tomorrow.
Yeah.
Okay, I'll just tell you. You guys are so sad. That's all. This is on tomorrow's quiz. Okay, this will be one of the got 5 problems. You're gonna have to find the sum of an infinite series by looking at the limit of the sequence of partial sums. The thing that we did yesterday. That was the very first example I did on the board yesterday, and you got it. You guys were following. You guys didn't pull a sock or anything like that. Okay, the first thing you should do is write out the terms. Okay, did you at least write out like the first 4 terms?
Yes.
Well, you got Marty.
I didn't know.
Read it off your paper. How can you be asking for both of them if you didn't even try it? Strike 1. 3 fourths. 5 36. 7 144. 9 400. See? Very good, Yaramari. Okay, now tomorrow, if you cannot even write out the terms, if you cannot even plug in 1, 2, 3, 4 and put plus signs in between it, just skip to the next problem, right?
How much do you get for writing out the term?
Nothing, you don't get anything. Now you gotta write the sequence of partial sums. Now if you write out the sequence of partial sums, you probably get a point there, or 2. Okay, what's the sum of the first term? You really gotta think about it. 3 fourths. Now add up the first 2 terms.
8 9.
Because you did it. Add the first 3 terms.
15.
Okay, see, this is the part. If you don't practice this, how the heck are you gonna do it tomorrow? I'm just gonna come through is the part. Add the first 4 terms.
Something over
24 over 25. Okay. So if by some miracle you get these numbers tomorrow, then you get 1 point. Okay, so this is the sequence of partial sums. Now you need to write an explicit formula for that. I'll give you a hint. Look at the denominator. There's like a use of body.
They're squares.
Yep. 2 squared, 3 squared, 4 squared, 5 squared. So what's the explicit formula? N plus 1 squared. Now look at the numerator. Now the other class, period 6, they go, oh, I got it. That's 1 times 3, 2 times 4, 3 times 5, 4 times 6. And they broke it down. But you really don't have to, because can you see that the numerator is simply just 1 smaller than the denominator? Do you guys even notice that?
Yep.
No, because I'm only looking at the problem for the first term now. So the top is just 1 smaller than the bottom. Okay, now what's the limit of that? If the degree of the top is the same at the bottom as the bottom, you look at the coefficients. 1! The answer is 1. What? Okay. Multiply out the, I'm not getting a response. Multiply out the top, multiply out the bottom. If the degree of the top and the bottom are the same, how do you get the limit? You look at the coefficients. 1 over 1 is 1. We just did sequences last chapter. This is like the easiest one when you have a rational function. Okay, Okay, that's what you have to do for 1A and 1B. You look at the limit, the sequence of partial sums. This will be one of the 5 problems tomorrow. I can't tell you any more, people.
What was this method called again?
Finding the sum of an infinite series by finding the limit of the sequence of the partial sums.
Partial sums. Okay.
That's all you do, looking for keywords.
Oh, yeah.
No, I know what you're doing. I used to do that in school. It only works up to a certain point though, you know.
Don't say add the first and second, add
No.
the first, second, third.
Yeah, but that's
You
what
know I
partial
meant.
sums are.
Yeah,
But
that's what I meant.
Okay, number 2. This problem is also on tomorrow's quiz. Okay, I will do one of them for you.
A.
Now, since 2B looks very similar to like the one I did yesterday,
Let's do A.
let's do A. 1 times 3. This is shameless. You guys don't feel guilty? Remoras have no feeling, Mr. Park. Okay, so the first thing you gotta do is write this using sigma notation. Now, the other class could not even get this. How many terms are there? Okay, this is what period 6 said. 99! Okay, thank you. There's 50 terms. What? How many numbers are there from 1 to 100? Would you agree half of them are odd and half of them are even? Okay, so look, 1, 3, 5, that's all the odd numbers, right? Gotta be 50 then, right? Or you counting them by hand, is that what you do? Okay, now, how do you generate the numbers 1, 3, 5? 2n minus 1. How do you generate the numbers 3, 5, 7? 2n plus 1. So, to get any points at all, you gotta get that, right there. Now, what did you guys remember 24 hours ago? What did we do yesterday? You multiplied it out. In fact, remember, didn't Hanaoka FOIL it yesterday? Multiplied it out? Okay, multiply it out and you get 4n squared minus 1. Now what do? You use those summation properties. What? You split it up like this into separate sigmas. When you have a plus or minus, you can make separate sigmas for each one. And then what about the number that's in the front here? What can I do with this? What can I do with this? Put it in the front. Okay, now, no, this is not. Now look at that. What is that? What does this mean, Mr. Park? Well, it means 1 squared plus 2 squared plus 3 squared, all the way until you hit 50 squared. Those are those 3 formulas we gotta memorize, Mr. Park, yeah? Yeah, but you're stopping at 50. So 50 times 51 times 101 all over. See, the people who did their homework know. So what happens if you don't memorize those 3 formulas correctly? Then you probably only get 1 point for this problem. Minus, okay, now this is where period 6 double. They got that, but they did. Mr. Park, what is this? Yeah, that means 1 plus 1 plus 1 plus 1 plus 1 50 times, right? So what's that? 50. And tomorrow, if you just write that on your paper, I'm going to give you full credit, and then the final answer is going to be like 1 bonus point. If you can compute this somehow, by some miracle, you compute that number. Give you 1 bonus point. Anyway, it's not that bad. Just start canceling. 2 goes into 4 2 times, that goes into that 3 times, 3 goes into 51, 17, and you're all set already, right? In fact, look, you can factor out a 50 if you wanted to. Or just keep staring like you normally do. Okay, now we move on to number 3. Okay, now 3A and 3B are like the same type of problem. Pick one, we're not going to do both, that's why, because we got to learn stuff today. 3A or 3B? Okay. Okay, I'll just do both already. We're just wasting time debating it. Okay, did you at least plug in 1, 2, 3, 4 and look for a pattern? Because all of these, that's what you have to do. You have to plug in numbers and there's going to be a pattern. And you got to figure out that pattern. Okay, so for A, Who actually did it? Hanaoka, should I call your name?
1 negative 1, 1 negative 1.
Okay, there you go. 1 plus negative 1 plus 1 plus. Do you see a pattern, or these are just random numbers?
There's a pattern.
There's a pattern, it repeats every 2 for Pete's sake. In fact, every 2 adds up to 0, Mr. Park. So if you have to add 100 of these together, what? What do you think the answer is? 0. Okay, but if you cannot even write out the terms, what prayer do you have? You have no prayer. Okay, what about B? Write out the first few terms. 1, 0, negative 1, 0. Why am I putting the 0 in? Just gonna have to put them all in parentheses. Plus 1 plus 0 plus negative 1 plus 0. What's the pattern in this one? Every 4 repeats. But you can't see the pattern unless you write it out. Some of you just want to like look and, no, you gotta write. So every 4, what happens when you add? You get 0. Every 4 adds up to 0. Oh, but Mr. Park, there's 50 of these.
20.
Yeah, so that means there's gonna be 2 left over, right? So what are the 2 leftover ones right there? So if you have 12 groups of 4, which adds up to 0, and these are the 2 leftover ones, what's the answer?
2 left.
Yeah, the 2 leftover ones. Can you please add them together? 1 plus 0, 1. Okay, now see, I already told you yesterday you have to use arcus theta. Do you think you're going to be doing that tomorrow? No, because I'm going to skip that problem, Mr. Park. Okay? You want to play that game? I'll play that game. Okay, so the first thing you want to do is change this thing into arcus theta. Change that. Change it from standard form to polar form. Now I showed you what to do yesterday. Draw the picture. If I go root 2 over 2 to the right, and then I go root 2 over 2 to the up, how far from origin am I? 1. That's r. Remember, polar coordinates r is how far you are from the origin. And theta is that angle right there. What is that angle? Pi over 4 or 45 degrees. I don't care if you write degrees or radians. Just write it. Okay, now what we gotta do is plug in 1, 2, 3, 4, 5, 6, 7, 8, and then add them all up. And the reason why you want to change it to polar form is because when you raise complex numbers to powers, you can use de Moivre's theorem. So if I plug in 1, what do you get? 1 is pi over 4. Okay, what happens when you plug in 2? How do you square a complex number? You square the r, which is still 1, but then you multiply the angle times the 2, and so you get pi over 2. Okay, now what happens when you plug in 3? 1 cubed is still 1, and then you multiply the angle by 3. Okay, and then you just keep on going until you hit 8, right? But then, again, you have to figure out what the pattern is here. Okay, let's draw a picture. This is in a complex plane now. This is a circle of radius 1. How do you draw this? Remember, a complex number is a vector in the complex plane. What is the length of the vector? And it makes an angle of pi over 4. So if you draw it, there it is. Hanaoka, no hoods at school. How do you draw this vector? 1 unit long, making an angle of pi over 2. How do you draw this vector? I see a pattern! What's the pattern? I don't know. Every 45 degrees you get a new one. What's up? What's up? What's up? What's up? What's up? Okay, so there's 8. What happens when I add these 8 vectors together? You get 0! Because this one cancels that one, this one cancels that one, this one cancels that one, and that one cancels that one. There's nothing left and you get 0. If 2 vectors have the same length and they point opposite direction, they cancel each other out, right? Even people in chemistry said they learned that. Something about, what molecule was that? Dipole? Is that a molecule?
No.
What is a dipole?
we learned that.
Is that a baby frog?
Not a pole type.
Whatever. Anyway, they said something about a dipole. Okay, now in problem D, Mr. Park, it's the same problem, but it's got these bars on it. What does that mean? Determine it.
Like
No, that means the length, because remember a complex number is a vector. So when you have a vector with the bars around it, that means you find the length of it. Well, what's the length of this first vector? Here. 1. What's the length of the second one? 1. What's the length of the third one? They're all 1. So what happens when you add 1 plus 1 plus 1 plus 1 8 times? You get 8.
8.
Okay, now E, this is the one that separates the sheep from the goats. Do you think you can see this one tomorrow? My pretty. Okay, before we even start, does everybody remember the greatest integer function from Algebra 2? I even told you it's the greatest integer function. Okay, let's review.
Oh, is that the step one?
Yes, very good. You guys drew the graph last year. It looked like this. Yeah, what the, what the, what the, what the. Remember that?
Yes.
I just memorized the graph for the quiz, Mr. Park. You gotta understand how this thing works. Okay, what's the greatest integer of 2.3? It's 2. It gives you the biggest integer that's less than or equal to the number. So what's the greatest integer of 2.97? It's 2. What's the greatest integer of pi? 3. What's the greatest integer of negative 4.53? Negative 5. What? Okay, let's look at a number line. 1, 2, 3, 4, 5. Okay, here's negative. Okay, remember on a number line, the negative numbers go this way, right? Negative 4.53 would be right about there, yeah? What is the biggest integer that's less than or equal to it? Like on, to the left of it. Negative 5, that's right. Please don't give negative numbers, Mr. Park. Okay, now we know how it works. Okay, so all you gotta do here is plug in 1, 2, 3, 4 until you get 100 and add them up. That's all you gotta do. Okay, plug in 1. Plug in 2. Square root of 2 is 1 point something. Greatest integer is 1, right? Plug in 3. Plug in 4.
2.
Square root of 4 is 2, right?
Yeah.
Plug in 5. Square root of 5 is 2 point something.
2.
6.
2.
7.
2.
8. But what happens when you plug in 9?
3.
Now you get 3. 10. 11. 12. 13. 14. 15. 16.
No,
No. No.
no.
When you plug in 16, you get 4. Okay, do you see a pattern here? Or these are just random things going on? You have to plug in enough numbers so that you see the pattern. Okay, so how many 1s are there? I just wrote it. There's 3 1s. How many 2s are there? There are 5 3s. How many? Wait, 2. This is 2, dummy. How many 3s are there? There are 7 3s, and you can see the pattern now, right? 9 4s, 11 5s, 13 6s, 15 7s, 17 8s, 19 9s, and how many 10s?
1.
Yeah, there's only 1 10. How come?
It's only 200.
Yeah, because you stop at 100, fool. I mean, class. Once you plug in 100, you stop. And then you just add them. You guys can add them up, right? Now, I'll give you a hint to the test, which is next week, Thursday, probably. Usually I put this problem on the test. I just change that number on the top. Like last year, I think it was 1,000. No, it wasn't 1,000, it was 10,000. Something you can square root kind of easily, like the square root of 10,000 is 100. What would I do if that number was like a big number? Just gonna have plenty of these in Mr. Park.
Make a series.
Yeah, then you use that series thing we just learned, right? Like number 2 on last night's homework. Okay, we got a lesson today. Today we have to learn, how much time do we have? Well, we could finish a little early, but that's not happening. Power series. There's actually only 2 more lectures. tomorrow is the last lecture already, then we just gotta practice. And believe me, you need to practice, because some of you guys are just gonna get blown out of the water in this test if you don't. This test is just chock full of so many things, that's why. What is a power series? What does it say in the notes? Here, let me just tell you. This is a power series. That's a power series. So what is a power series then? A power series is an infinite, fill in the blank. No, that's not geometric. These A's are constants. What if the constants are like 1, 1, 3, 5, 7? That's not geometric. I mean, yeah, it's not geometric. A power series is an infinite blank. Fill in the blank.
Hang on.
Oh no.
Thank you. Polynomial. You redeemed yourself. You guys even know what a polynomial is? That's when you have x to whole number powers. Like x squared, x cubed. Remember we studied polynomials, x to the 4. And the reason why we study power series is because polynomial functions are the easiest functions to work with. Now in this chapter, you have to memorize 5 power series, and they're all in the notes, okay? Here's one of them. Cosine x is equal to 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus dot dot dot. Now I can't prove this to you because you actually need calculus to prove this. So if you take BC calculus next year, you're going to actually prove that this is the power series. But what we're going to do is we're going to memorize the 5 the 5 basic ones, and then we're going to do stuff with them. That's it. So you got to memorize this, people. There's lots of things to memorize in this chapter. So if you don't do your homework and start memorizing them slowly, then you try and memorize everything all at once for the quiz or test. It's all over but the crying already. Okay, now just to give you a visual picture of how power series works, take out your calculator. Take out your calculator. If you want to do it on your iPad, you can. That's fine. Put it in radian mode, like it should be. So what we're going to do is we're going to graph this. y1 equals cosine x. Okay, and then we're going to compare it with the power series. Okay, but let's just go a few terms at a time. So y2 equals, and let's just use the first 2 terms only. 1 minus x squared over 2 factorial. But we know 2 factorial is 2, right? I hope. 2 times 1.
Function?
Yes, function mode. Does that look like polar, parametric, or sequence? What kind of question is that?
I thought POL was polynomial.
Not police.
Squared. Divided by 2.
Okay, now let's graph. Why don't we do a zoom decimal? Zoom 4. Go. Punch it in and do zoom 4. Unless you have a prism. What do you notice about the graph? Well, cosine x looks like, come on, we know what cosine x looks like. It looks like this. Woo! But then what happens when you graph this? This is just a parabola, right? Reflected over the x-axis, a little bit wider than normal, and then shifted 1 unit up. What happens when the thing graphs the parabola? What do you notice? What are you noticing? It's like, yeah, it's like over here, the graphs are almost identical. Yeah. I mean, not the obvious stuff, like they both have the same y-intercept. Okay, now this is the same concept. Okay, how many of you are in AP Physics B? I keep asking this question, yeah? Oh, you're not Mari?
Yeah.
Yeah. Okay. This is the same concept. Do you ever do problems like this? For small values of x, sine of x is approximately x. Because the other class told you. Yeah. Or for small values of x, tangent x is approximately x. And that's because, look, the graph of sine x looks like this, right? Here's sine x. Woo. What does the graph of y equal x look like? Woo! For small values of x, those graphs are like almost identical. So when you use small, and those of you taking physics next year, this is how you get dominant. So, but sine of x is hard to compute, so that's why instead of x, sine x, you replace it with x, and that makes the computations easier. But that only works for small values of x. What about tangent? Tangent looks like this, right? Woo-hoo-hoo-hoo. Here's y equal x. For small values of x, the graphs are almost identical. And that's the same concept we have here. Here's cosine x, and here's the graph of 1 minus x squared. Look, almost identical. But the beauty of power series is it doesn't only work for small values of x, it works for all values of x. But then you gotta use all the terms though. Okay, so what would happen if you add the next term? Plus x to the 4th over 4 factorial. Okay, add that term in and try graph this now. Now you get a 4th degree polynomial. Leading coefficient positive. So now the graph will look something like this now. Woo! Yeah, but look, the thing is just fitting almost perfectly onto the cosine graph. You guys get it? Okay, let's just go as many as we can then. And let's just minus x to the 6 over 6 factorial plus x to the 8 over 8 factorial, which is, Chai? 8 factorial. Okay, minus x to the 10th over 10 factorial. Quack, 10 factorial. Just mumble your way through it. For those of you who don't know, you could just write 10 and then factorial, right? Because you know where the factorial button is, right? In the probability menu. Oh, probability! I thought that was the... I'm trying to think of a word with PR and B in it, but it's not coming to me. The parabola menu. It's no parabola menu. The problem menu. Okay, just punch this in and graph it. So now you got a 10th degree polynomial like this, and then it fits like this. It fits like a glove. Look at that. Don't look at that. Look at the one on your calculator. Anyway, the more and more terms you use, the more and more the graph looks like cosine. So if you want the exact graph of cosine, you have to use an infinite number of terms. So if you have an infinite number of these terms, then the graph will fit the cosine curve exactly. Why do we even study this, Mr. Park? Just so teachers have jobs? No, I already told you the answer, just like in physics. For small values of x, it's the same, right? Polynomial, and it's just way easier to work with polynomials than transcendental functions. So that's why, and you're gonna see when we start doing calculus on this in a couple weeks. It's way easier to do calculus on this than on that. Oh boy. Okay, so what kind of problems are you gonna see tonight? Okay, so here we go. So you might see a problem like this. Write the power series for e to the 2x. Well, the first problem on tonight's homework is you're going to have to write each power series using sigma notation. That's pretty easy though, I think, right? Okay, let's do an example. Are you guys going to actually pay attention to the examples this time? Okay, here's the cosine one. So, I guess the first order of business, you guys got to start memorizing these. What? It's easy. You know why it's easy? Because cosine is an even function, isn't it? Hey, got all the even powers. Oh, that's the only way it can be even. Sine is an odd function, so if you look at the sine power series, hey, got all odd numbers. That makes it easier. Okay, write this power series using sigma notation. So this is what you do with tonight's homework. You write sigma, n equal 1 to infinity. Now, the first thing you notice, positive, negative, positive, negative. How do you make it alternate? Negative 1 to what? N or n plus 1? You want the first one to be positive. Okay. Now, if you rewrite the 1 as x to the 0 over 0 factorial, then I think you can kind of see the pattern now, right? I hope you remember 0 factorial is what? Okay, how do you generate the numbers 0, 2, 4, 6? Hey, that's arithmetic. Common difference 2. So x to the 2n and then adjust. If I plug in 1, you want to get 0. Minus 2. And then, hey, Mr. Park, the power and the number in the denominator is the same. So 2n minus 2 factorial. And that's how you write it using sigma notation. Okay, the next set of problems is now you gotta manipulate power series. This is gonna be the hardest part for you guys. Especially if you don't do your homework. Okay, so let's do the one here. Write out the power series for e to the 2x. And just write out the first 4 terms, good enough. Well, there's lots of ways to do it. One way is go, hey, isn't that the same thing as e to the x quantity squared? Okay, and do we know the power series for e to the x? Yeah, it's written on the thing. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot dot dot. And then you just square it, which means you multiply it by itself. There's plenty of writing in this chapter. You guys remember how to do long multiplication? You take the first term, distribute. You take the second term, distribute. You take the third term, distribute. You take the fourth, distribute. That's what you do. You're going to be doing a lot of long multiplication and stuff unless you can find a shortcut. Yes, there is a shortcut for this problem. So that's one thing you can do. Another thing you can do is, you know the power series for e to the x. Instead of thinking of it as e to the x, think of it as e to the box. So the power series for e to the box is 1 plus box squared over 2 factorial plus box cubed over 3 factorial plus dot dot dot, right? So if you want to write the power series for e to the 2x, just think of that as the box. Like this, 2x, 2x. 2x, 2x, and then just simplify and you finished already. Isn't that a lot better than doing long multiplication? So you really gotta think, because if you don't think, then you're gonna end up doing more work than you're supposed to. Oh yeah, Mr. Park, I'm not doing it anyway. Okay, wait, what about tangent x? I think this is one of tonight's homework problems. Okay, right? I think the problem is write the first 3 terms in the power series for tangent x. What would I do?
Cosine.
Okay, now,
Over cosine.
these, okay, what did you say?
The 2 power series.
There you go.
We have.
Tangent is sine over cosine. Do we know what the power series for this is?
Yeah,
Yes, what about that?
I think so.
Yes, and what does this bar mean?
Divide.
Divide! So, what is the power series for sine x? X minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus dot dot dot. And you divide that by the power series of cosine, which is 1 minus x squared over 2 factorial minus x to the 4 over 4 factorial minus x to the 6 over 6 factorial. And then you do long division. Mr. Park, is there a shortcut? No, not for this problem. That's how you do it. So you can probably bet on the test or the next quiz, not tomorrow's quiz, but of course I'm going to give you problems where you got to do long multiplication and long division because anybody can do the shortcut way, right?
How do you do long division again?
You mean the thing we've been doing since Algebra 1? You're going to go back to your algebra teacher and say, can you reteach me FOIL? It's like the same thing. This is like easier than FOIL. Okay, here, I'll start you out. 1 goes into x how many times?
X.
And then you just keep going. Okay, then you take this and multiply it by the divisor here. So this times the divisor, what do you get? X minus x cubed over 2 factorial plus x to the 5 over 4 factorial, oops, minus x to the 7 over 6 factorial. And then
Try.
you subtract, this is just like regular division. Subtract. You guys just want me to do the problem right now, don't you? Is that it? Okay, you subtract. Okay, let's just do the first term then. Subtract. Okay, you know what would be easier? If you change 3 factorial to 6 and 2 factorial to 2. I'll give you a hint. When you subtract fractions, you gotta make a least common denominator. Which is, so we got negative 1 6 minus negative 3 6. Which is what? Negative 1 6 plus 3 6 is 2 6, which is, oh yeah, you're right. Okay, then you gotta subtract these two. And then you start the process all over again. 1 goes into that how many times? If you can't figure that one out, people, you know what? You know why this problem is easy? Because that's a 1. If somebody were to ask you 1 goes into something how many times?
So,
Yeah, come on. If that's not a 1, then the problem becomes a little harder. And then you just keep on going until you get 3 terms. See, I did 2 of them for you right there. You have to write 3 terms.
oh, we're gonna have to. Oh.
Wait, let me look at the homework. Yeah. And then the last part of the homework is just some more series to keep you, I don't have it, just some random series just to keep you in it. Oh my gosh. Now there's only one more lecture, which is tomorrow. I'm just gonna give you a preview. For those of you in physics, tell these other people why this is important. This is the thing we're gonna learn tomorrow. If this is the graph of time versus velocity, so let's say that this is the velocity graph right here. Why did I do that when I got it there? What is the significance of the area between the graph and the t-axis? Mari.
Displacement.
Yeah, that's the distance that the particle traveled. If this is the graph of velocity versus time, that area tells you the distance the particle traveled. So, it is very important to be able to compute this area. But see, when you take baby physics like you guys got right now, the only graphs that you get are like this, yeah? Oh, or right? Because that's the only way you can compute areas. Oh, that's a triangle, I know how. Hey, that's a rectangle, I know how. That's a triangle, I know how. Okay, but what about like a shape like that? How do you find the area of that? And that's why Sir Isaac Newton invented calculus. Because he knew that this area will tell him the distance traveled by the particle, but he had to figure out how to compute that area. And that's why he invented calculus. And that's why he's one of the 3 greatest mathematicians of all time. So tomorrow we're going to learn how to compute that area. Well, a little bit. Okay, we're done. The bell rings in 2 minutes. Oh, I thought we were going to finish early. Oh,
Who are the other 2 mathematicians?
Gauss and Archimedes. You remember
Them all.
Dimov? You'd probably be in the top
20.
100.